Hi everyone, and welcome back to the next session of our Blockchain Community Day 2024 conference. We are back with two extra sessions today, and this time we are going to continue our Technology Day with the session dedicated to the topic of recent techniques used in zk-SNARKs, together with our friend and colleague Michal Szczepanik.
Hello and welcome everyone.
Yeah, hi, how are you?
You enjoy the conference.
Yeah, thank you so much for joining, and thank you so much for applying such a great topic. I think it's a pretty hot topic nowadays, and I'd like to remind our audience that Michal is our regular guest. We've been conducting a couple of other sessions dedicated to smart contract obfuscation, dedicated to Web3 world for mobile developers back in 2023 and back in 2022. And please check out other sessions together with Michal Szczepanik. And this time we are going to continue the topic of zk-SNARKs. And without further ado, I'd like to ask to share your PDF file to the screen, and I hope we can now see it. And I'd like to remind our audience to leave your questions in the live chats where you're watching this video, and at the end we will go through the questions. I think the floor is now yours. Good luck to you, Michal.
Thank you. So hello and welcome one more time. So as was mentioned, we will be talking about recent techniques used in zk-SNARKs. So let's start our discussion. Yeah, and maybe I will start with the introduction of myself. My name is Michał Szczepanik. I work as solution architect at EPAM. Also have PhD from Wrocław University of Science and Technology. I'm a big fan of AI. That's why I have two AI bots with avatars you can see here. One is with Dunning-Kruger effect. The second one is like my dog, so cannot be controlled. I'm also a big fan of the Lego, so that's why sometimes you see some stuff here. And yeah, let's back to the topic. So we have this interesting topic as zero knowledge, and maybe remind everyone what are these algorithms and why we need them. So zero knowledge proof is something which generally power the innovation right now in many cases, because we are not only talking about the blockchains, but cloud computing, machine learning, and many other fields. So the scenario which can quite easily show us the problem in real life is the fact that sometimes we go to the bar, and we are asked to prove our age. We need to show our ID card, and instead of age, we present the whole birthday date, and at the same time, they can see our name, surname, and some other data which we don't like to share. And this is something where the zero knowledge can works quite well, because instead of, let's say, providing all the data about yourself, you need to prove that you have age which allow you to buy this specific drink, so 18 or 21, depends on the law in your country. And we have, let's say, two parties here: the prover, so the person who need to prove something, and the verifier, who need to verify if the data are true, and we can really buy the stuff. So having zero knowledge kind of proof, we theoretically should provide information. I can do this. To represent it in maybe more visual way, let's move to some where is Wall-E kind of game, where we have books, and books has the pages. And here I see, here is Wall-E. Let's say that this is Wall-E. The other people, so I see all the context. I see everything, number of page, but do I need it to show to someone to prove that I found this guy on this picture? Probably not. So let's maybe do this in more ZK way. So instead of presenting the whole picture, We can put the wall in the center to even hide where he is in case of the screen, and hide the rest of the image. So we only show, okay, I found this smiley face, and this is enough. Okay, let's move on and discuss the thing which is important for us. So different zero knowledge algorithms. We have zk-SNARK and zk-SNARK as the most popular things. So we get zero knowledge, Succinct non-interactive argument of knowledge, and which is SNARK, and in case of SNARK we have scalable transparent argument of knowledge. So we have these two solutions which are different a little bit between each other. So the SNARK is the older one. It was first time used for some, let's say, in blockchain, zk-Cash in 2016, and SNARK is quite new. So comparing them, we can say that, okay, zk-SNARK is created to prove the single message and require something like trusted setup. In case of SNARK, we don't need this trusted setup, so we don't need to share any keys. SNARK, on the other hand, is much bigger regarding proof size, so more expensive, and a little bit longer regarding the proving process comparing to the SNARK, which is much lighter. And this is one of the reasons which probably cause that this is more popular, but at the same time longer on the market. And if we will take a look at the list of available ZKP systems, so zero knowledge proof solutions, we can see that, okay, most of them based on zk-SNARK, and even some of them upgrade the solution for zk-SNARK in the way that this quantum secure issue which appears in general for this solution is let's say upgraded, and we theoretically are secure from the upcoming quantum revolution. We are not sure what will affect us first, quantum computing or AI. So we will see. But yeah, back to the SNARK. It uses elliptic curve pairing, so something which you may know, you may not, but we will try to cover it somehow. It's small and quick from the verification perspective. So generally, this is the biggest achievement of this kind of solution, because we can really fast verify if everything is okay, and at the same time we can it not cost us that much. That way it's quite popular. Also, if we take a look at the comparison which we had previously, the popularity we can see of zk-SNARK we can see in Polygon, Aztec, zk-Sync. From the SNARK perspective, we have Starkware, which is quite interesting zk rollup solution and called StarkNet. So this is the thing which we can consider if we also comparing these two algorithms, not only the things which we see here in the table. But back to the SNARK, as I mentioned previously, we need trusted ANDs, so we need to share request a short key, and some people name it toxic waste, which maybe is some kind of true. Okay, we need some kind of trusted infrastructure, but we don't need to exchange that much data, and not quantum resistant, potentially upgradable cause that this is still a popular solution and used in many cases, which I mentioned previously. But okay, we have this solution. What next we need to think of is the way how we can prove the things. And here we also have additional algorithms which we can apply to make it easier to provide only these specific pieces of the data which we like, or generally not show the whole knowledge which we have, but only confirm that we have it. We have, for example, some kind of solution, or we have some kind of access, specific parameters, etc. Like, for example, our age is on the level which allow us to do some specific things, like we mentioned in the first example. So one of the options, and I think the one which starting to be more and more popular, not only in case of blockchains and zk knowledge, but in general, is the GKR protocol. So the name of protocol comes from the authors of the article which was published in 2008, but in totally different discipline. They were focusing on some decision trees and stuff like that. So mainly boring stuff. And at some point, let's say the readers of this article find something awesome, which is the practical use of it. And this GKR protocol was first used in 2015 to verify the stuff, and it used also some check protocol inside to process it. So the plus of this kind of protocol is the fact that this is really high efficient and secure method to verify complex computation without, let's say, compromising the privacy. So we don't need to, let's say, show everything. We only need to, let's say, be asked by the verifier about some elements of the solution to prove that, okay, we know it, and we know the right answer. To describe you this approach in a little bit more human-friendly form before we will jump to some interesting math stuff, we can start with this discussion about these two guys which we see on the screen. So on the left we have prover, on the right we have verifier, and here we have some magic puzzle box which we would like to solve. To solve these crazy puzzles, we need to click the buttons in specific ways. So we don't need to, let's say, provide the whole solution step by step, but we can be asked by verifier for some specific steps, or generally part of the steps, totally randomly. So the logic around GKR protocol works in the way that, okay, the verifier asks me, show me how to press that button, and the prover, the button is totally randomly selected, and the prover do this action to prove that he knows exactly how to process with this specific step to solve the puzzles. Then the verifier chooses another button and process this again and again and again. We reach some point that we go through all, let's say, levels of solving these puzzles, totally selecting totally randomly the step which is needed on this specific level to discover that, okay, he go from the bottom to the top to address everything. in right way, for selected elements in correct way, and this gives us this proof that this prover know how to solve the puzzles without presenting the whole solution to the verifier. So we can still, let's say, hide most of the information at the same time, because this check is done totally randomly. Someone else cannot, let's say, repeat our steps, or generate the probability that the steps which we just provide will be asked again is really low. So theoretically we can ignore that fact. Okay, so this is the one of the most interesting algorithms, quite old one, but nowadays everyone is talking about it for different trends. So let's move to a little bit mathematical aspect of it. If you are scared of the math, this is the time to maybe consider some other presentations, but I would like to share with you some mathematical aspect around it. I hope I will do this in enough clear way that you will be not that scared. First, we need to think about multilinear polynomials. So the things which are polynomials that are linear in each variable. And one example of this kind of things is equality function. So equality function is something which generally these two values are equal when each element inside each pair of elements with the same ID will be same. So practically we can get one or zero as a value. So if we imagine that this is, let's say, only one element, we can say that, okay, if they are both one, then 1 multiple 1 is 1, plus 1 minus 1 is 0, 1 minus 1 is 0, so this is 0, and we get the 1 as a response, which is correct. They are equal. In case where they are both 0, this one is 0, here we have 1, here we have also 1, so 1 multiplied 1 is 1, so we still get the 1. But what happens if they are different? This will be 0, 1 minus 0 is 1, 1 minus 1 is 0, so it will be also 0, so the whole thing will be 0. So theoretically any other operations are not needed, because we discovered the elements which are not equal to each other. And we have, let's say, a little bit more complex aspects, so multilinear indicator function, which generally give us this possibility that we have chains of similar values on this linear function, and we generally do the analysis in a way that if these two are equal, we get 1. If this is not equal to x, we are getting 0. That's it. Quite easy thing regarding the basics of math, which we need later on. And the equality function is used quite often is generally used in GKR. And another thing which we need to consider is sum check, which generally gives us this opportunity that prover has poly with small degree, a small I put 3 here, in each variable. Prover wants to prove to verifier that sum of each x of this function is equal 0. So we can do the sum check protocol between P and V, reducing the climb to the climb of function of R equal V for any random R in this discipline. So generally, we can do some kind of reduction here quite easily using sum check, and these two combinations allow us to generally do the thing which I mentioned on this image. So we randomly select some values, and based on that, we can be sure that the prover know the topic. And quite important statement, which sometimes is mentioned as a bad thing, or generally considered, okay, we need to do some crazy mathematics here. No, reduction doesn't require P to do any fast Fourier transformations or even commit to other polynomials. It's generally rather not true. Let's name it like that. We have some extremas, but we don't need to consider them. Regarding the application and how we can use it, so zero testing, P would like to prove to V that function of x is equal 0 for all of x. We choose some random beta, which is in this function, define the function of x, which is equal, which use in addition of equality function, and try to prove that that kind of function, which is practically much easier to do and implies the desired climb of f's, which give us this possibility. So generally, we convert zero testing to some kind of sum check, and that's it. So we really simplify the problem. But what in the we have also something like polynomial commitment. So when prover sends some short commitment of h to multilinear polynomial h, the verifier choose some specific r, and P send back the z, which is equal of function of r, and together with some short proof like open f of and r that z is correct, and this is enough. And as I expecting, you have a lot of math right now, so let's go a little bit crazy. Let's try to do the zero testing with multilinears function 1, 2, and 3, and having the verifier who has commitment of f1, f2, and f3. So we generally would like to prove something like that. And how to do this? We can do this quite easily using GKR. So practically GKR, considering the fact that committing to the polynomial is quite expensive, but we can use, I'm answering this question right now, sum check for polynomials that we don't have commitment to. And yeah, we can, because we can do some magic trick with generally the idea of this algorithm. We do summing, reducing, and then random evaluation at the end to get another sum check over the different poly, and this gives us the possibilities to make the complex sum for really large polynomial to generally have the proof of really reduced number of values that we need to commit to. So generally, we have this randomization to reduce the number of elements which we need to prove. And if we take the example from Justin Teller from one of his articles, if I'm not mistaken, from 2013, something like that, we have this kind of structure. So generally, we try to prove this statement. So P wants to prove to V that correctness of this kind of statement. But how to do this? We can quite simpler define the multilinear function G, where G is G of 0 is something like that, G of 1 is something like that. So generally we are representing the statements on the inner layer here, and based on that we can claim that this is equal to U, which we defined previously, and having that statement, we can avoid to compute the commitment to full G by simplifying it using a multilinear function, which is a quality function, and having the previous math. I know that you probably just forgot most of the stuff which I mentioned. Expecting that is quite late. So shortly we can convert h of r to this kind of function, which is much easier to prove, and having in additional the thing that we can convert and define g of r as a sum over the f. We can define the equality function f functions and equality functions. Additionally, we can generally use the sum check to verify this kind of structure, which we know, and based on that, based on that, we can prove the elements of the middle layers or one of them, and using sum check protocol, we can reduce evaluation of g of r to function of r2 for any random r2. And doing that, the verifier can quite easily verify that they are equal. But how to do this? It has commitment function and can ask P to check if the function of R2 and 0 is the value of it, and function of R2 and 1 and the value of it, which prove the correctness of the knowledge which we have. Okay, we don't have a lot of the time, so really sum up. The GKR protocol generally gives us the inputs. Based on that, we have linear interactions where we do the random selection of the elements which we need to prove for each, let's say, layer of this kind of tree, which defines the knowledge. Then we apply the sum check, which generally allow us to prove that we have the knowledge, and final verification is done when we process all the layers, and verifier perform the final check to on the reduced problems. The thing like that can be used, as I mentioned, in many scenarios, including the blockchains, the fact that, okay, I need to that I have something, and this is, for example, not in blockchain but stored somewhere else, or I need to prove that machine learning works correctly and has the correct knowledge without, let's say, reviewing or hold this model. The same, it can be used for cloud computing to solve some problems. So guys, that's all from my side. I know that we are almost run out of the time, but thank you very much if it was interesting for you, and back to the studio.
Okay, yeah, thank you so much, Michal, for making this topic so interesting. I mean, the slides and the content was very good, and I really enjoyed.
You mean the left part, because the math, I think most of the people okay.
Still, I believe there will be some questions after we publish the recording, and I will let you know about.
To share the
Yeah,
questions.
feel free to reach out to Michal, and feel free to leave your comments or feedbacks in the comments where you're watching this video. And I think that's it for now, since we need to move on to the next session. Thank you so much, Michal, once again. We're always happy to see you on our stage.
Thank you. Have a nice one.
Okay,
Bye.
and we are going forward with the next session. We'll be back in 15 seconds.